Okay, well, welcome to the Air-Sea Fluxes from Space webinar series. Today we have Lisan Yu, who is going to tell us about OAFlux2, resolving global air-sea fluxes and budgets with satellite and in situ observations. So, and I'll let you take it away, Lisan.
Okay. Um, okay. Thank you, Sarah. Hello, everyone, and I'm glad to be here. Today, I'm going to talk about OAFlux2, and I'm the lead PI for the project for the past 20 years. And OAFlux2 is the second generation, which takes about 10 years in the development. So I start with this figure, which everybody knows about the process involved in LC exchange. And mostly is a short wave radiation, long wave radiation, precipitation, vibration, which gives out both vapors and heat, sensible heat, and of course the wind. So as surface, and these processes regulate the ocean and atmosphere interaction and also the climate. But quantify these fluxes are not easy task, and none of us can do all of these fluxes. So those, I'm sorry. And you probably already know that radiation is done by the series teams, which produce both top of atmosphere radiations and also radiation at the LC interface. And the precipitation by the GPCP groups. And most of you probably still remember what we hear from them last week. And the OA flux is about the turbulent fluxes. We quantify the exchange of heat, moisture, and momentum fluxes using satellite data and also get help with individual observations. Okay. And our group is not only one doing the LC turbulent fluxes. And this is many, and here is an overview of the many groups we do the similar things, like guided GSSTF, HOPES, IFMR, and G04, which the PR probably the one going to give us a talk next week, and the C-Flux. On the bottom lines are the OAFlux version 1 and versus version 2. So those flux products are done by the independent groups across the world, but some of the products in recent years are no longer updating. You can see the ending years for each product. And we also phasing out the first version as we put a lot of effort right now on develop a second generation of the products which have a better resolution and a better algorithm for retrievals. And the period is for the satellite from the 88 to now, which we produced at the end of the last year and still continue production. So the main topic of today is about around three lines. And first, we're talking about those like the methodology in developing the fluxes, and also the observational gaps that still limit the accuracy of LC flux estimate. And second, once we have products, people most ask, how do we do in terms of closing global surface energy and freshwater budget? So I'm going to give an overview of current progress and the key challenges achieving this budget closure. And also talking about where do we stand in terms of this budget closure. And the last, I do emphasize put some emphasis on the ALC fluxes in the policies, and which is our recent progress in terms of improving Arctic ALC flux estimate and in understanding what drivers of this energy budget. As you know, the surface fluxes are the only very limited direct observations of surface supreme fluxes over the global oceans. And to produce global maps, we have to use these parameterizations. And the parameterization for the momentum fluxes are here, which you can see just like depending on the drag coefficients and also those winds. And then because we're using satellite winds and satellite winds relative currents, we can simplify the equations to just U10, which is neutral equivalent winds at 10-meter height, and adjusted to the individual observations. And for sensible flux, we have these equations, and some people use 10-meter air temperatures. If you reference is ship observations, you probably set is higher. But since we use buoy observations, so we set at 2 meters, which is also in line with the NWP model output. And the latent flux is a similar thing, and we need humidities both at 2 meters and also at surface, which is based on the temperature. And evaporation is related to latent flux because evaporation process release both heat and also vapors. And because of that, we often see that energy and freshwater budget are linked because of the evaporation is a central link of these two cycles. So clearly you can see that from this parameterization, we need input bulk variables like winds, temperature, humidity, and SST. That sounds simple, but if we look at the equations, and there is turbulence coefficients, CD, CH, CE, for momentum, heat, and moisture. And the parameterization and these coefficients controls how efficiently the ALC exchange of this momentum, heat, and moisture would be. And the parameterizations is about to parameterize and to better parameterize these coefficients. And here, just uncertainty, because this parameterization depends highly on the roughness length and also on the stability correction functions. And the left is about the equations. You compute the drag coefficients. And those roughness length stability correction functions depend highly on the surface conditions, such as wave breaking, whitecaps, and the sea spray. And also those select parameterizations rely on Monod-Uphoff stability in similarities theory the most, which assumes a well developed layers, which in the logarithmic wind profile. And this need the well developed layers breaks down in extreme conditions like strongly stable or strongly turbulent state. And plus, we always have the problem at direct observations of fluxes, especially in extreme conditions, which make improvement or refinement of these fluxes very difficult. And some people may be wondering, how much uncertainty can flux algorithm introduce? A few years back, I conducted analysis, which I use the fluxes, compare the fluxes in their native algorithms from the 4 fluxes, from 4 NWPs, EI interim, NSEP1, NSEP NCARI analysis, which we named NSEP1, and CFSR, and the MARA1 is not MARA2. So the left one compares the NWP fluxes in original format, which is a thicker line, and also the fluxes use NWP variables applied to the standard core 3.2 algorithms, the thin line in the same color. And that picture pretty messy. So I compared their differences, which is NWP in original form versus enthalpy variables in the standard format. So you can see that the difference is quite significant. The NCEP one, which shows the largest difference, around 30, 20 to 30. And EIA interim is which is the red, which is closest to core, but still shows large variations in the tropical subtropical region, and the differences can be around 10 on average. And so here is the map of the global distribution of the uncertainty. And I use 12 products and mostly NWP and reanalysis because they shows uncertainties in both algorithm and the variables. And the satellite fluxes are mostly computed from the core, which we cannot see the impact of the algorithm on the error contribution. And clearly, there are kind of two areas worth attention. The first is, of course, is a large error, is global boundary currents, is particularly a crustal extension and also Gulf Stream. And in that places, AOC grid is so big and also the system so dynamic and the flux algorithms and also the variables are hard to agree. So they have mean average errors, uncertainties, the difference standard deviation between the mean is more than 30 watts per meter square. But second area is a broad region in the subtropical area between around 15 to 30 degrees latitude in both hemispheres. And in these regions, and the northern hemisphere seems like have a broader and even larger amplitude than the southern hemisphere. So if you look at the red panel, which shows zonal average, the black one shows the standard deviation, and the red is the mean. And the peak occurs between the 10-degree north to 40 degree to 10 to 40 degree north, which corresponding to the larger area on the left panel. And obviously, the degree of the direction and depend on the amplitude of the mean fluxes. So we have the weaker fluxes at higher latitude, also the smaller STD. But nonetheless, the subtropical errors is a region cannot be ignored. But in this region, there are very few data to validate. So enough about parameterization. And another error source is the input back variables, which our group put a lot of efforts in developing develop better algorithm for retrieval. And in among these four algorithms, TA and QA, which air temperature and humidity, cannot be directly observed from satellite because they do not interact or emit electromagnetism, and that can allow them to be sensed. So they are inferred from breaking temperature in the water of oxygen absorption channels. And the right figure shows the microwave absorption spectrum, and on which you can see a few peaks like water around 22 gigahertz, oxygen around 55, and also another peak of water around 183. And these frequency channels are used by the satellite sensors for developing the water, vapor, or temperature profile measurements. And that is also the channels we use in inferring the relationship between breathing temperature and the surface humidity temperature. But this relationship between the integrated, the TB basically measures integrated water vapor and temperatures in the total atmospheric column. So the relationship between TB and the body temperatures and the surface air temperature and the humidity is highly nonlinear and relies on individual measurements at the ground truths. And we have different methodologies in terms of developing the retrieval algorithms. So because our methodology differences and the retrieval algorithms vary, and which lead to the varying degree of accuracy in terms of temperature humidity retrieval. Nonetheless, two main challenges for these two retrieval algorithms is like how to separate boundary layer variability from the vertical integrated humidity temperature profiles of variabilities, and that depends on your algorithm. The second is the limited variability of individual measurements in high latitude and the coastal regions, and that's really constrains your ability when you develop those retrieval algorithms. And this will see the gaps in current buoy measurements. And the SST panel on the right, on the left, which align those like buoys over the SST mean contour. And you can see the buoys and the courses as OAI buoys in recent years. And the buoys in green dark mostly come from the global buoy observations in the tropical region. So outside tropics, there's like a few of like oceanside buoys, but there's not too many. And there's a gaps around SST of 15, 16 isotherms, and which there's none, and there's very limited observations. And on the right top, I shows distribution of the buoy based observations, flux observations with respect to SST. And please note that the vertical axis is 10 logarithmic base 10 base 10 in terms of base 10. So, and you can see that there's a gap around 15 to 16 degrees of SST, and also at the lower SSTs. And those numbers only about hundreds. I mean, there's only about 100 of observations of these turbulent fluxes. Of course, we do not include OI, which once include OI, the number will be increased. And if we compare these observations with products, and clearly there's a gap around 15 degrees C, and also it shows that the differences between products and the buoys are mostly in the tropical region, which is consistent in the high latitude, which is a tropical region, and subtropical region, which is consistent with the picture I showed previously. So, and at OAFlux, we actively explore the methodology and advance the methodology or techniques which can improve the retrievals of TA and QA from satellite. And here, and we apply the data-driven methods like machine learning. And the picture shown here and how the machine learning framework works compared to EIA5 and the OAFlux a multivariate regression, which we published in 2018 paper. And the buoy used to train the model is showing on the left, the most tropical forecast. And you can see in the tropical region, subtropical region, and once you look at the pictures that, oh, machine learning model doing a great job because it's similar to while about basic structure, and also giving really fine details about the LC, the humidity distribution in the tropical region. However, if you do the zonal average, and you can see the variation, the differences between the algorithms is in the tropical region. And that's region, that is why, because the model is trained by the tropical region, tropical buoys. So it does pretty well in the tropical region and retrieve those non-linearity. Everything is doing great. But when coming to the high latitude, because there's no individual observations to train the model, tell the model what to do. So the model uses the tropical information and to simulate the high latitude humidity. Of course, it does not work. That's why you show that is machine learning with this buoy-based, tropical-based database is breaks down at high latitude. So, and we in order to improve this machine learning model, we put a lot of effort to pull in the NDBC buoys and also sail drum measurements that cross those 15, 16 degrees ST boundaries and also covers high latitude and coastal regions. And we have 50 buoys along the Eastern Pacific and the West Atlantic. And the effort is pretty rewarding because look at the red panel, we can see, and now with high latitudes are much better constrained once we have those enhancement at high latitude and also coastal region. So, and now here is a major challenge with data simulation model as the interface is that models are only as good as the data they are trained on. So, and the individual observations hold a critical importance in the next step when applying machine learning models. So now let's move on to what we have in the OAFlux2. So here is a comparison of the OAFlux, the first version versus the second version. And for the flux components, we have sensible and the latent fluxes and evaporation. And for the OAFlux2, we also have vector winds and surface stress. And the resolution is 1/4 degree versus the 1 degree before, but temporal resolution is still daily because we do not have enough satellite data to cover higher the daily resolution. And duration, we have a satellite period. We are not planning to go back because we have no satellite. We cannot apply the methodology backward. And global coverage, we have a global ice-free ocean. And in addition, we have ice-free and also ice-covered regions for surface stress. And for the approach, for previous version, we kind of optimal blended satellite and reanalysis. And for the OAFlux2 is satellite derived. And for winds, we merged from 19 sensors, including both microwave wind speed and also scatterometers. And for QATA, and that is the previous version, is used basically on the NWP models. And for this version, we retrieved from 15 sensors. And we retrieval algorithm is including 2 methods, linear regression and also machine learning. And we are refining and consolidating the machine learning and try to finalize the data this summer. And for SST, and we make use of OSTEER, which have a better resolution and also better accuracy. And algorithm, we use a core 3.6 with some modifications. And the validation, we use the validation, but the validation is mostly validates about variables, not the fluxes, because the bug variables do not provide fully independent validation. And we're using the same kind of algorithm. And I just go quickly about algorithm, and the total number is nearly 500,000 points included on a daily basis included in the comparison, and the accuracy is pretty satisfying for us. So, and once products, you want to see how the global field look like. And here, this comparison between our old version and the new version. And the OAFlux 1 degree versus Escape 2.5 degree are currently online. And the 2009 is the last year. That's the Escape early version and on that year. So we compare that year just for the comparison purpose. So you can take off any year and give similar pattern. And for the annual mean basis, and the red indicating the ocean is gaining heat, and the blue is showing the ocean is losing heat. So this annual mean, and which you mean the last picture is similar, but apparently the early version is a lot warmer, which shows the ocean received a lot more heat in the early version. And for the freshwater fluxes, and we show on the left, we show the 20-year mean from the OAFlux2 versus iMerge, which is 0.1 degree resolution, and the comparison between top and the bottom, and which shows the early version and the current version, and the mean structure clearly are very similar, and it shows the evaporation zone and versus precipitation zone in the tropics. The only difference is the magnitude. For each centers, we see the evaporation center is higher than the previous version, and also the precipitation center, magnitude is higher than the previous version. And the real contrast is on the comparison of short time scale. It's like a monthly mean, and here it look like a monthly mean, and you really see the improvement of resolution on the structures of immense P distribution. And for the coast resolution, we only see the broad, very general pattern, but for the final resolution, we do see very details about those like weather phenomena and associated with weather events, and also evaporation regimes. And we see those like a kind of eddy-like structures inside of it. And now come to the second topic. Once you have products and you want to ask how your product contribute to the closure of the global ocean surface energy budget closure. And here is the budget closure, which requires those like everything add up equals 0. And this is really challenging because QNet involves those like short wave, long wave, sensible, and the latent flux. Each of the terms is greater than 100 watts per meter square meters. And when you asking, they add up to 0 globally, and that really means those large terms, when they combined, they come towards, they cancel each other and towards 0. And that's challenging because any small errors and biases in any one component can lead to substantial imbalance in the net budget. And the figures here shows the comparison of the products, our versions versus Cflux and versus NWP models, 6 NWP models. And you can see NWP models are not all balanced at the surface because NWP model reanalysis a balance at the top of atmosphere. So the surface balance not really affect their model performance. And the surface is basically constrained by SST force. So, and here comes from the imbalance of these products. And for the satellite products, I compared the Cflux versus OAFlux. So Cflux's version is original format, which shows about 22 watts per meter square imbalance, which is comparable with our version, first version. OAFlux is around 20-something watts degree. However, Cflux have another version which shows a near balance with near balance of of surface energy budgets over globe, ocean, and for our OAFlux2, and we also balance, and we come about 5 watts per meter square. And this comparison, except for the Flux, are taken from the website, and for other products, you found the 10 years between 2001 and 2010. And we come to this balance without any adjustment. It's only improvement of QA retrieval algorithm and also modifications to flux parameterization. And for Flux L 2015 is from the NASA's new integrated analysis platform that applied a budget optimization methodology. So in this approach, imbalanced input budget components are objectively or optimally adjusted within their uncertainty bounds using constrained optimization. So the adjustment is about global, including both land, ocean, and high latitude atmosphere. So the adjustments minimize residual while enforcing conservations of mass and energy across atmosphere, land, and the ocean domains. So, and that comes very nicely to a near balanced budget for after adjustment. However, if you see the partitions of this balance, and you see it's very interesting problem, which is you can get to the balance with and in many kind of combinations. For example, say Fluxes original form is shown here, but the adjustment and the increased increase the turbulent fluxes, but reduce radiation. And the OAFlux2 versus series is both higher, than the flux in terms of turbulence components and the radiation components. And we have no artificial adjustment in getting to this level. And the good thing is now the OAFlux versus CI5 and is kind of quite similar in terms of global energy budget balance. So here is multiple combinations of radiation and turbulent fluxes can satisfy energy budget balance. So, and we really need to identify the physical realistic partitions, what is best partitions among these products. And we need additional constraints. So the other constraints is freshwater budget. And because we know the freshwater budget and water cycle budget is linked, the energy budget and freshwater cycle budget are linked through the evaporation processes. And here's a look at overview of the global ocean freshwater budget. And on the table on the right side, we showed those compiled those major studies in past 20 years. And you can see how their E and the P and R versus those total budget in terms of swordrop. And the scatter plot on the right shows how the line towards those line about the dash line. So the dash line is 1.1, which really shows the E versus the ratio between E and P, which if we count for the E contributions to global evaporations, 86%, and the P contributions, ocean P contributions, global precipitation, 7% is 1.1. And you can see all the products line pretty much on this 1.1 dash line, so which is internal consistency. But Reno, which is companion studies within NASA's new I framework, and they both use optimizations to achieve closures of freshwater and energy budgets, and is consistently weaker than our Fluxes versus iMerge. So iMerge and uh, emerged as an independent data set in our comparison, along with the previous one and the series. So series and I emerged from the two different groups. We try to align our OAFlux2 with both, and we so far we're pretty successful, and we can close budget to nearly 0.05 threshold, and which is very which is very good, very satisfying to us. So, and this picture shows the time series of the energy budget and the freshwater budget in the middle panel, and also wind stress. And that shows we not only about global balance, but also we can capture the major interannual variabilities associated with El Nino, for example. And for the surface, and for the 2000, between 2000 and 2015, and the line, I mean, the budgets are pretty flat, and there's no much of not much variations except in the annual perturbations. But we see the major peaks in 2016 El Nino, and about two water per meter square imbalance. And about this imbalance coming down in recent years. And we also see the peaks in the P minus E in 2016, which shows the ENSO is big influence on the energy budget. And for the P minus E, we have a time series in the 90s, which shows a trend which is decreasing in the P minus E over the decades, but in the later decades is pretty flat except in recent years, and probably the trends will be coming back in the coming year, I hope so. But for the wind stress, and it's pretty stable, and except in the decades of 90s, and the trends in the recent 20 years is pretty stable despite the warmings and in the global climate. And so and that is our budget. And so we want to see how the seasonal change in QNet, and especially the seasonal reversals in the net heat flux, which is key characteristics of the climate change, climate system, and it shows ocean response to delayed response to forcings, surface forcings like slow radiation. And that is the 3 monthly means in, again, use 2009 in August, September, and October. And in August, which you can see the Southern Ocean still in the summer, and we still see a lot of radiations, a lot of net heat. The ocean gets a lot of heat from the atmosphere, but the Southern Ocean is losing heat. September is transition period, and the heat gain in the northern hemisphere has been losing up, has been relaxed, and the Southern Ocean starting to pick up to some heat from the atmosphere in October, and we see the complete reversal pattern from the August, which Southern Hemisphere receiving the heat, and Northern Hemisphere, especially the Gulf Stream region and the crustal extension regions, have losing a lot of heat. And with this backdrop, and now we can see the change in the Arctic Ocean, which is a recent study we have put a lot of effort on. So for the for these panels, and we show the Arctic regions, and on the left is topography of the Arctic Ocean, and along with names of each basin. On the right, the top row shows QNet from our recent products versus series EBAV, the QNet, and this mean of 10 years. And you can see here is also the sharp transition in the QNet from August to October, which shows complete reversal from heat gain in the total Arctic region to heat loss by October. And September is transition period. We see some areas gain heat, but weak heat, weak warming, and some area tends to losing heat now. But if you compare or analyzing QNet products in the Arctic Ocean and for the 12 mean, mostly from analysis, and you can see the variations between the mean products is quite large. And August, the mean is quite weak, and it shows that the variations is around 10 or less, except in the Norwegian Sea area. And for the September, and that's the month in transition, and the differences between products quite significant. Actually, the standard deviations, the magnetic standard deviations, even larger than the mean background, the total mean of net heat flux. And for October, and when ocean picking up the total heat loss, and also the differences among products is quite significant. It's more than 70 watts per meter square among these 12 products. So we have observations, but in situ observations in the Arctic Ocean is really rare. But the good thing is, like, we have a recent NASA program which is assessing in field camping, and the SESI is about salinity and certification, and the CS Edge experiment is conducted in September, from early September to early October, and which focus on study on the dynamics impact of salinity anomalies caused by melting sea ice. And along this cruise, they have LC flux instruments that include infrared and the shortwave radiometers for measuring downward long wave and shortwave radiation. They also have two air temperature sensors and two relative humidity sensors. Unfortunately, those relative humidity sensors are both failed. So they assumed a constant relative humidity of 8-9%, given the low temperature in the Arctic. That is a reasonable assumption. And they also have two sonic anemometers, which recording wind speed and direction. And this data are available as 20-minute average from JPL PODAC. And now we see what can we see from the observations. And this panel are the heat fluxes computed using core algorithms. And on panel A, and we see strong diurnal cycle. So diurnal variability in downward solar radiation are really strong, particularly in the early days of the cruise. And but this amplitude reduces rapidly towards the end of the cruise. And meanwhile, there's a long wave radiation, downward long wave radiation with the blue color background, which show no clear diurnal sign. Pretty stable. And for the long wave radiation, and there's no any apparent diurnal variability. The only magnitude of the change in the magnitude of latent heat flux. They're negative because that shows ocean lose heat to the atmosphere. On panel C is net surface radiation, including both up and down, and both net long wave and net short wave. And clearly you can see that is blue, which is net radiation loss be increasing with amounts going on, and also the diurnal cycle amplitude reducing fast towards the end of the cruise. And total turbulent fluxes, again, there's no much of diurnal variability, but increased amplitudes towards the end of the cruise. So the panel E on the left bottom, and it shows the surface heat budget to the budget. And clearly you can see, and the cruise have two stages. The first stage, we can see strong diurnal cycle, and the gains during the daytime and the loss during the nighttime. And towards the end of the cruise, and that is Arctic state is completed the heat loss regime towards the end of the cruise in the later September and early October. And so in this plots, I compiled downward solar radiation I mean the diurnal cycle or downward radiation, and the color indicate the days. Each line is color coded by the date, and you can see from the beginning and towards the end of the cruise, and those amplitudes of downward radiation has reduced very rapidly. And from the beginning, about 375, peak is 375 watts per meter square downward to around 25 watts per meter square by the end of cruise. So the QNet also shows strong diurnal cycle driven by the solar radiation, and the QNet's beginning is past the domain in these hours, but by the end of cruise is mostly negative, still weak diurnal viability. So if I collect the peak of solar radiation and downward radiation and make this diagram, I can see the downward radiation is reducing at about 10, 11 watts per meter square per day. And that and the Q net, total net, is also driven by the downward radiation. It also decreases about 11 watts per meter square, which is the pace of decreasing is quite similar between the two, which shows the dominant forcing of solar radiation. So how our flux is doing compared to the cruise? And the first part of the cruise is pretty much near the ice edge. You can see this like a cruise picture from the top left. And so that is a bubble seas region. And the comparison is a little bit difficult. And you can, the red is our daily, the thin line is a ship hourly, and the thick line is a ship 12 hours running mean. And our oil flux comparison is the black. So we do very well once the ship away from the marginal ice zone, but we kind of not able to come down to the ship levels once in the marginal ice zone because the Fluxes is 25 kilometers area average, and the buoy, and no, the ship is just 1 point of lines in the whole ocean. On the other hand, there's a solar radiation shockwave net shockwave radiation from the series doing pretty good. The black, and the long wave radiation shows a little bit of directions from the cruise track observation. And the wind stress is really great. We're doing really well in observing the wind stress along the cruise track. So here is the surface energy shift around the autumn equinox, which is astronomical seasons. And what we do here is integrate energy budget along ship track, because we want to see how the total energy accumulations during the ship observed by the ships. And the first is downward radiation, and you can see the total energy, solar energy accumulations pretty steadily increasing, and until those September 22nd. And for the net radiation, they show a turning point around September 22nd, which is October equinox, the date of autumn equinox. And for turbulent fluxes, we do not see strong sign change, but increased accumulations of turbulent heat loss once we cross those like autumn equinox. And the total net heat flux, which is interesting, we definitely see the regime shift once we cross the September 22nd, and which is a date when the sun angle change around that day. So the ship track is only along a line, and we want to know how does the ship track measurements is representative of over the region, at least in the Bubble Sea or Chuck Sea region. For that purpose, we use our fluxes and together with series to make up the QNet. And we did the area average and then compared and then plotted the time series from the May, and from May we began to see ice melt. We have the data once melted, and then we through the time until the end of December, and when the data points or there's no open ocean data point at all. So, and clearly for the net fluxes, we see the turning of the net heat, net radiation around those September 22nd, and the turbulent fluxes. And we obviously we can see the enhanced turbulent heat loss around after September 22nd. And for the total net, we come up this pattern. It's before September 29th, we have Arctic Ocean gains heat from the sphere. After that, we have the region lose heat to the atmosphere. So that is area for the ship, NASA SESI ship track observation. And that observation, that 1 month really did well in terms of capturing the shifting of the season. And to further along analysis, we integrated energy budget over the area, meaning the map showing on the left, and see how the energy accumulations throughout the year in this area. And clearly, we see a change, a turning point in the accumulated energy around those like September 22nd. And that is closely along with the astronomical seasons. And the top, it shows the face of the Earth towards the sun. And I just took out because the sun circulates around, the Earth circulates the sun at the angle of 23.5, something like that. And I just take the face for each season at the top, compile them together and align them lines with the change of the fluxes in this area. So we can see in the summer solstice, we can see in the Arctic Ocean begin to gain heat starting from the points, and by the autumn equinox, the accumulation of heat reaches the peak. And by that time, and we're starting to see the turning and the ocean starting to losing the heat. And by winter solstice and December is steady, because that time we do not have open ocean data, we cannot really see that. But apparently, and the Arctic seasonal transition is closely linked to the astronomical seasons, and it's driven by solar radiation. And that is a paper led by our summer students, Joe Carrick, and published in last year in JGR Oceans. And during this time, you may wonder how the change of turbulent fluxes are influenced by this like solar radiation or these astronomical cycles. And on the left is the shape observations. And we can see that in the there's like a TS which is in red, and the TA is in air temperature is in blue. So we can see severe cold surges in the time series, and each of the cold surges along with coincides with like a southward winds. So, and this means whenever you see the wind direction change, you see the cold surge, and it give you the large increase in the turbulent fluxes. So that means northerly or north winds is a major region for the change of the fluxes in the Arctic Ocean. So why is that? From the September 22nd, autumn equinox, because the wind is basically westward, But in September, that means the background is air temperature, air sea temperature differences. So after that, in September, for example, in 20 seconds, the strong peak, and we see the winds from the poles, strong northerly wind from the poles, which directly southward and bring the cold air. And that is 730s, which is clearly the case. And on the right, with turbulent fluxes on the background, and you can see how this turbulence, how the turbulence changes along the wind path, wind surge path. So, and in the Arctic Ocean, and the solar radiation is a driver of the energy cycle change, and the turbulent fluxes is response through the air sea temperature differences and the change of wind direction. So in terms
We've
of
done just about 5 minutes left.
Okay, in terms of winds, I'm going to close in 5 minutes. In the winds, I briefly introduce about the ocean surface stress from the tropics to polar seas. And now we have the wind stress. We can cover not only global oceans, but also Arctic Ocean and Antarctic Ocean, which on the left, which shows the winds and the wind directions. On the right, and also on the bottom is Ekman pumping rate. So we can calculate in the Arctic Ocean, and we see pretty much downward, and in the Antarctic Ocean, we see pretty much upward. So, and the basic idea is like in the open ocean, we see there's like LC exchange and the momentum exchange, and which pretty much can be detected by the spectrometer. But on the ice, we cannot observe tall IW, ice water interaction. Stress we cannot observe, but we do have ice motion. We cannot observe AI, which is air ice stress, but we do have the ice drift. So we can use parameterization and using a quadratic drag law to compute those fluxes, and also these are the common mean that is for ice covered area, and that's the equation. And that equation we can use in these products to compute those like ocean surface on the ocean surface stress on the ice cover. And that is some movies which shows how those like change of wind stress and equipment pumping rates in this Arctic oceans on daily basis. And you can see a lot of change along the ice edge, which is indicated by this by black lines. And last slide, we show the winter time change in ocean surface stress in the buffer seas, and clearly surface stress and it's changed dramatically in the recent decade. You can see the 2 decades in recent last 10 years versus the early 2000s, and the stress has been increased, and the sea ice drift, which shows here, is coherence change, and geostrophic currents tend to be increased slightly because of increased stress, and here the pattern of the change in this page. Do not have time to discuss more, and we have 2 papers on the review, and led by my postdoc Charlie. So summary and the conclusion, and I go through quickly about methodology, and also discuss about gaps observations that affect the better estimations of LC fluxes. And I also go through about closing ocean surface energy freshwater budget using fluxes, and how very sustained in terms of budget closure with other products. And for the LC flux in the policies that our focus in recent years try to improve Arctic heat fluxes by integrating certain observations, and also to understand the budget change in the Arctic oceans, because that is critical for understanding the Arctic warming and amplification effect. Especially right now on the ice melting, there's a lot of ocean open for LC interaction. So, but we identify the uncertainties in the marginalized zones, which we need more studies about this area. But in any way, and OAFlux now is to now have just like ice covered and surface ocean surface stress cause both ice-free and ice-covered regions in the polar oceans. And we also have a 36 years of 36 or 37 years of fluxes of heat, moisture, and the wind over the global ocean. So I stop here and thank you.
Well, thank you. We are just at the end of an hour, so I know that some people will have to run off, but maybe if the Oasis staff are available, we can take a couple minutes for questions if people have any before they have to go. And if not, we will let people email you with questions separately.
Sure. Yeah. Thank you.
So I don't see any questions, and I know people are going to have schedules that make them rush away. So thank you so much for a really engaging talk, and I'll urge people to send their questions on to Lisan directly.
Yeah. Thank you. Bye now.
Thank you. Bye.